Hello, F Sharp. Welcome back for another edition of Fast F Sharp, where we are currently working through improving the performance of the topological sort algorithm, specifically the cons algorithm. And as I mentioned before, this algorithm is at the heart of a piece of simulation code that my company has been developing. And so the performance of it is critical. Our goal is to be able to sort 1,000 graphs within 500 microseconds. And last time, where we left off is we had made some improvements and we've actually gotten it to 5 milliseconds. So we still have a ways to go, but we've made some really significant improvements. We're about an order of magnitude faster than where we started. When we started, we were at 54 milliseconds. Now, and you can see the benchmark on the screen, at version 4, we're at 5.4 milliseconds. And let's review real quickly the changes that we made last time. So the big change from last time was that instead of using F-sharp records with strings as the values inside of them to store the names of nodes, we instead opted to use ints and int64s with units of measure. And the reason we wanted to do that is because we noticed that hashing was kind of dominating the runtime of our algorithm. Most of the work was actually spent computing hashes and then making updates to hash set and lookups in dictionaries. So we decided to use types that were really great for hashing. Now what we want to do, though, is we need to go even faster. We're still an order of magnitude off from where we would like to be. So what do? We profile. Instead of guessing where the problem is, we're going to do some measurements. And the program that we're going to use is .trace. And I am going to use .trace. I'm pointing it at our executable, and I'm using the argue library, ARGU, for F Sharp to provide command line arguments for it. And I'm saying, hey, I want you to do the profile task. In this case, I want to profile method 4, which is the benchmark that we were measuring last time. And I'm going to have it perform 2,000 iterations. And the reason I want it to perform many iterations is because I want the CLR to really hammer on that method and optimize it as much as possible. And I want to get a realistic view of what that performance will be when it's used in a simulation, which would be calling this 1,000,000 times. So go ahead and save. I'm going to say start. And what this does is it starts the program. It creates an instance of the benchmark class, and then it runs that method version 4 2,000 times, and it's collecting sampling data of what is taking all the time. And now we're going to be able to look at that and get a view of where our algorithm is spending its time. So the screen comes up, and first thing I do is I kind of zoom in here into the main method. I then look at profile and I see, okay, it's running our method v4, which corresponds to the 4th version of this algorithm that we've created. And we see it's taking 91% of the time, which it's expected that it wouldn't be 100% because there's startup code that has to run. So inside of it, first thing I do is I look to see if there's any particularly hot method or function that's taking most of the time. And I see here, I got the loop, and I got the create the initial edge set. So let's look at where those are in the code. So I'm here at version 4, and I'm going to go ahead and scroll down. So create initial edge set is something that's taking quite a bit of the time. And it's creating an instance of hash set. It's then iterating through these values and adding them to the hash set. Okay. I see that. And then I also see loop here. So this is what runs after we create the initial edge set. We then run this loop. And what is the loop? This is the loop right here. So this is the code that's running. And so this is what's recursively just processing through the nodes in our graph. And I will link to the Wikipedia article that describes the cons algorithm, but this is essentially as direct of a translation I could make of that to F Sharp. And basically what it does is it visits a node, adds it to the sorted list, removes the edges coming out of that node, and then looks at the children to say, hey, does that child no longer have any parent edges? And if so, then it adds it to the list of nodes that it needs to process. The key thing, well, so that's the work that's going on. Let's go back to the results of .trace and let's kind of reason through what's going on. And my desire with these videos is to kind of help take you on the journey. I could just skip to the end and show you my ultra mega optimized version, but what I'm really wanting to do is to help you develop the thought process for being able to look at profiling information, benchmarking information, and then synthesize that and figure out, okay, what is it that I need to do to make my algorithm go faster? So what I am doing now is I'm looking at these method calls and I'm trying to look for the things that are really hot, things that are taking a lot of time. What I'm noticing here is that, okay, reverse accumulator, so it's processing through a list. Again, we have reversing a list. That's not very much time there though. To list, 10% of the time. That's really significant. That's quite a bit. So now what I'm doing is I'm coming down here to look at the subsystem. So I'm going to go ahead and click on the method, which is the top level for the code that I'm interested in. And I'm observing what subsystems are dominating the time. And I'm seeing here in user code, topological create edge set. Okay, I observed that before. Okay, create initial edge set. That's, again, just iterating through something and adding it to, it's iterating through a list right now and then adding those values to the edge set. And then in terms of collections, got hash set. I also want to look at some system code. So what am I observing here? Well, value collection, enumerator, move next, iteration, hash set, find item. So I'm looking at this. There's nothing that's really standing out to me in stark contrast. There is this to list that's pretty egregious. I really don't like that. And if we look at where that is happening, we get this list reverse here of the sorted nodes. And the way I'm accumulating in this loop right now is I am to create the sorted list of nodes for the topological sort. What I'm doing is I'm prepending the nodes to this list as my accumulator. But that means at the end, I have to do a reverse on it. Well, that's not really great as far as performance goes. I would rather not have to do the work of reversing a list. There's another thing I notice here that I'm looking at benchmarks. And I haven't talked about what these columns are over here much, but I have been reporting them. And now is the time where I want to kind of dive into what these things are. On the far right, we look at how much memory is being allocated. Generally, you want to do this as little as possible because the more memory you allocate, that's the more the garbage collector is going to have to manage and deal with. So generally, you want this to go down to be better. These other three columns are really critical as well. Branch mispredictions, branch instructions, and cache misses. Let's start here with branch instructions. So the way the processor is working is it's going through your code and there's points where it has to make a decision where it has possible branches it could go down. So like an if statement, if X, then do, if condition 1, then do work 1. If condition 2, do work 2. So the CPU is having to make some decisions about, okay, I'm getting to a branch. There's two different ways I could go. And the way CPUs work is that they do branch prediction. And so what it will do is it will start executing code down a branch to try to get ahead of you. But the problem is if the CPU incorrectly predicts which way you go, it will cause a misprediction. And when you do a misprediction, you lose a lot of work and you have to reset. I don't have time to really go into that, but it's definitely something worth going to. I'll probably do a video at a later point where I talk in more detail about branch mispredictions. But the important thing to know is that the fewer branches your code has, the easier it is for the CPU to figure out what work it needs to do. And so it's better at scheduling the work that it needs to process. It also means there's fewer opportunities for it to make an incorrect prediction. Whenever it mispredicts, that's a potentially huge performance penalty. So generally you want branch instructions to be lower. That means your algorithm is going to be easier for it to analyze. You then want to have fewer mispredictions. As few mispredictions as possible is really what you want. So this tells you a little bit about the logic of your algorithm, is how well is the CPU able to kind of figure things out and optimize its execution. So lower is better for these two columns. Cache misses are another huge issue. So again, I don't have time to go into really deep detail about it, but your CPU, that core, has several levels of cache, and then it has main memory. So I'm working with a Zen 2 processor. It has an L1 cache, an L2, an L3, and then it has to go to system memory. And if data is in the cache, the CPU is able to access that incredibly quickly. But if the data is not in the cache, it has to go out to main memory, which is extremely slow compared to the cache. So a cache miss happens when the CPU needs some data, it looks in its caches, it's not there, so now it has to go out to main memory. Now, the CPU does everything it can to prefetch data for you. And again, it's trying to guess like what it is that you're going to need. And so it will be bringing data into cache as intelligently as it can. But if your algorithm is very difficult for it to reason about, it's going to have misses. It's not going to know what information it needs. So highly predictable code is advantageous. One of the heuristics that a CPU uses is locality. It assumes data that's near each other is often accessed together. So data locality is critical. Let's look at our code. List. We're using a list here, and I'm going to zoom in. I watched one of these videos on my phone the other day, and I realized I'm not zooming in enough, so my apologies. But a list in F# is a linked list, which allows for really beautiful, elegant algorithms, but can be absolute murder in terms of performance, because that linked list could have a pointer to just anywhere in the heap, which means the CPU has no chance at being able to figure out intelligently where the next piece of data is in that list. So linked lists, are possibly one of the worst data structures when it comes to data locality and therefore cache misses. So this is not me saying lists are bad. Lists are fantastic and can be absolutely the right choice in a lot of situations. When you need to go as fast as possible and data locality is critical, we should be looking for a different data structure. And the data structure that has the best data locality of anything is an array, because an array is basically just a contiguous block of memory. It's all there right next to each other. So what I'm seeing here, so what's the mental leap that I'm making toward the next optimization that I want to do? It's generally, I see cache misses and I would like that to go down. I see branching and branch misprediction, and I would generally want those things to go down. I look at .trace and I see this toList call taking 10% of my time. This tells me, I should look at swapping a list out for an array wherever I can, because that's going to give me better data locality, and it's also going to allow my algorithm to be more predictable for the CPU, because the CPU loves to think in terms of arrays. So what do? So for version 5, what I do is I'm going to change some things up. And I want to put these side by side so you can kind of compare and contrast. And let me take version 4 to the top. So I'm still using int and int64 with units of measure for kind of modeling the values of my domain. But where things change is down here. Oh, I'm going to have to zoom out. My apologies. Is when it comes to how I'm actually storing the information in the graph. Instead of read-only dictionary, I am going to be using a type called a bar. Now, what is that? So I did a video earlier that I will add a link to in the description where I talk about one of my favorite collections, which is what I call a row, which is just a wrapper around an array. But what it does is it enforces units of measure on the index, int. And that allows me to use raw arrays and get the performance of a raw array, but get the type safety of saying, hey, you can't just use a raw int. You need to use an int with the correct unit of measure. And the reason that's important is because a lot of algorithms for going fast work on arrays, but it's very easy to mix up which integer you're supposed to be using for indexing into which array. At least it's very easy for me to mix those things up. So I created the type row, which is, like I said, just a wrapper around an array, which enforces units of measure on the index. And again, I will have a link in the description where I go into much more detail about that. So what is bar? A bar is a read-only row. And the idea that was in my head is like, okay, if I have a row of things, I could possibly rearrange something like an array. So that's why I use the word row. But a bar is typically just a solid thing. It's a solid, straight piece of something. And I often think about like a piece of metal, like a bar of steel. It's a straight line, it's contiguous, but it can't be rearranged. So that's why I use the word bar. So a bar is a wrapper around an array that enforces units of measure on the index. So you can conceptually think about it just as an array with some additional safeties. And then for the values that are in there, instead of having an edge list, I'm going to have an array of edges. And so the main transform that's happening in this entire thing is I'm getting rid of lists. I'm now using arrays and array-like things for all my data. And I'm making one other change. Down here, instead of, and I'm going to bring this down here for the compare and contrast. So for my sort, instead of using a list to keep track of what it is I need to process next, I'm going to use a stack. And also for keeping track of the sorted nodes, again, instead of using a list, I'm going to use a queue. And stacks and queues are actually just really convenient data structures that in .NET, the implementation is they sit on top of arrays. So again, I'm using data structures that have contiguous memory. And so what I'm doing is I'm trying to make it easier for the CPU to reason about what it's going to need in cache and what it needs to process next. So those are the only changes that I'm making here. And also means at the end, instead of having to reverse a list, I can just say, hey, take that queue and turn it into an array. So data structures that are friendlier to the CPU. Note, yes, I am using mutable data structures, but they do not leak outside of this function. So I'm still providing the user the immutable guarantees that we come to expect when working with F# libraries, but I'm taking advantage of that mutability to get speed. So what does that do for my performance? Great question. So when I do that, I get a doubling in performance, much faster. What's interesting is, you remember how I talked about branch mispredictions and cache misses? So this is where things are going to get a little interesting. And we're going to kind of keep coming back to these metrics. We noticed that allocations went down significantly, which is fantastic. And we kind of expect that, because using a queue, using a stack, and instead of the lists for keeping track of what work to do and what the sorted order is, they are going to incur much less allocation. So this is great. And that generally means less allocation, better performance, generally. We see that cache misses have gone down from 159,000 to 132,000. Now remember, this benchmark is performing the sort on 1,000 graphs. So if you wanted to know what this number is on a per graph basis, you just divide by 1,000. So on average, we had 159 cache misses for a single graph. Now we're down to 132 cache misses. We have almost half the branch instructions, which again is a general metric for saying how easy is it for the CPU to reason about your code and therefore optimize it. But we see that branch mispredictions have gone up, which would generally mean worse performance. But our benchmark says, no, you're much faster. So this will start to tell you about the performance implications of cache misses versus branch mispredictions. Generally, you want both of those things to go down. What's interesting is sometimes you'll have to pull a lever and like, yeah, okay, I'm going to reduce my cache misses, but my branch mispredictions have gone up. And sometimes that's the right call. And when, in this case, what we see is that our performance did improve, even though those levers went in two different directions. So what does this mean for you? What's the takeaway? Code that is cache friendly and low on branches will generally perform better. And sometimes you can't optimize for all the different metrics, and so you have to pick and choose which one is most important. And in this case, cache misses are more important for performance. Like reducing those is more important than reducing the branch mispredictions. And that's just because of how expensive a cache miss is versus a branch misprediction. Cache misses can be hundreds of cycles. Branch mispredictions can be, depending on the architecture, like 20 to 30 cycles. Again, it really depends on your architecture, but they're both bad, but generally cache misses are far, far worse. So reducing those is more important generally than branch mispredictions. Now, we're still only getting started. Like, we got a long way to go. I hope you find this interesting, and I'm really excited to unpack more of this for you. And again, this is kind of one of those important steps that we need to make in order to keep improving our performance. And so what we're seeing here is that making data contiguous can dramatically improve the performance, because it's going to reduce our cache misses and therefore make it so that our CPU isn't stalling, waiting for data to be brought in. So thank you so much for spending some time with me today. I'm really looking forward to the future versions of this and just showing you just how far we can push this. So until next time, keep writing that awesome code. Thank you very much.